So thank you very much for coming to my talk. My name is Paolo, and I will be talking about nature mostly, not kernel development. No, no. My talk is beaver dams and kernel development, but this is about the topics that I will touch. A small recap on the confidential computing technologies for x86, a small status report for what's up with upstreaming the TDX parts, and actually the bulk of the talk will be on how distros can help developing user space parts for TDX. So stuff like kata containers is developed for TDX, but testing it and even developing can be hard if all the code for TDX is not upstream yet. So I will talk a little bit about that. Again, nothing extremely technical. I have some slides in the beginning that describe SMP and TDX, but that's just to show off. So what is confidential computing? Confidential computing is basically about guaranteeing confidentiality and integrity of virtual machine on untrusted hosts. Some of you will probably have heard of confidentiality, integrity, and availability. Availability is not covered by confidential computing because the host can always just decide to not run your VM, and that kills the availability. Like, there's only so much that you can do about availability. TDX comes from Intel, SCV SMP comes from AMD. They have the same goals and completely different implementations. The goals are basically the confidentiality and integrity, and to encrypt the memory so that the host cannot see it, to protect the guest state so that the host cannot change it, and protect the page tables to prevent some other attacks that I will go into detail later. So about my memory encryption, both are done at the memory controller level. Intel's using something they call multi-key total memory encryption. It's something that is not limited to virtualization. There are some key ID bits in the page table entries, and in principle, you can just configure your keys using the pconfig instruction and use it in bare metal code, except that Linux doesn't support it, but still you could. AMD has a bare metal encryption that is mostly to prevent offline attacks or the so-called evil maid attacks or stuff like that. And that's called secure memory encryption. But specifically, the multi-key ability is tied to virtualization. SCV, secure encrypted virtualization, associates the key ID with the address space identifier of the virtual machine. And that's why you cannot use it on bare metal. You always have to go through nested page tables in order to have the virtual machine address space ID. Configuration is done through a separate processor, which on Linux is also a separate device node. And it's done. It's available in Linux through ioctls, and there is a command protocol between the main x86 processor and the secure processor. It's not done through special instructions. However, SCV alone cannot do much, MKTME alone cannot do much, because the hypervisor can still capture and modify the register state. You will sooner or later have private keys or encryption keys in registers, so you just read them, and the host that you didn't trust has your key, which is not optimal. Another thing that you can do is a replay attack, where you modify the EIP address, or you can just set a breakpoint and move EIP past the code that checks, is this the correct password, or something like that. So you need to protect the guest state. The host must not be able to watch the registers and modify them. And the way to do this is a bit complicated, because some VM exits actually need access to the execution state. For example, if you want to read an MSR and the MSR is provided by the hypervisor, you need to know what MSR you are reading, and that is in a register. So if a VM exit is synchronous with respect to guest execution and needs access to execution state, talking especially about SCVS here, it will actually be redirected to an exception handler in the guest. It will not be handled by the host. The guest will copy in an encrypted memory a small subset of register state that is used by that instruction. For example, in the case of read MSR, it will put the number of the MSR in unencrypted memory. And it will issue a special instruction that's called VMG exit on AMD, TDVM call in Intel processors. And that instruction is guaranteed, of course, to get to the hypervisor, can do its thing, send back the result, and it will be copied back to the register state by the guest exception handler. Exceptions are different for AMD and Intel as well. The protocol is different, but the idea is basically the same. Finally, SCVS-MP is where things get serious because SCVS is also susceptible to some of these attacks. SCVS-MP, I will start with the AMD acronym, it's Secure Nested Paging. And that's because it basically limits what the translation from guest physical address to host physical address can do. The hypervisor can, with the SCVS, do memory aliasing attacks where you take some memory and later you put it in multiple places, and therefore you can basically copy memory from one part of the other space to the other, and the guest will not notice. There's also memory remapping attacks where you can choose the context, the contents of some pages. Like you know that some page is all zeros. Even if you cannot read it, if you know that it is all zeros, you can just map all zeros whenever you want. Or if you know that maybe with some collaboration from something malicious running the guest, that you know that there is an op or something with known contents of memory, you can map it and place it where where you want and divert the execution flow or change the private keys if you can smuggle them inside the memory somewhere. Like without SMP, you cannot really guarantee neither the confidentiality nor the integrity. And this is done by tracking of page ownership. A given page, this is more for AMD, but the same ideas kind of apply for TDX as well. Each page is either owned by the hypervisor or owned by the guest or owned by the system. In the case of AMD, for example, the virtual machine save area, which is where the register state is stored, is a system page, and you cannot touch it essentially. System basically means that it is assigned to the secure processor and the microcode in the case of AMD, or to the TDX module in the case of Intel. What is the TDX module? The TDX module is basically how all these things are implemented for TDX. Let's start with AMD. However, you do have a couple of instructions, one for the host RMP update, one for the guest pvalidate, but really the bulk of the interface happens between host and guest on one side and secure processor on the other. There is this interface that is available through ioctls in Linux. And also there is one of these VMG exits that just says, pass this block of memory to the from the guest to the secure processor, or this block of memory will be in encrypted memory. The host cannot read it, but the secure processor can. And this can be done to have some communication between the guest and the secure processor without the host being able to look at it. Everything is done through the secure processor. Instead, in TDX, you actually have x86 code that implements this. Sometimes you will hear this concept of internal, smaller, trusted hypervisor called the low visor. So all the important steps in running a virtual machine are done through the TDX module. All access to the VMCS is mediated through the TDX module. The private part of the EPT, the one for the pages that are encrypted, is done by the TDX module. And the TDX module does the VM launch, VM resume instructions, and therefore it also has the first look at what happens at VM exit. It can handle it itself or pass it back to the host. It can decide to inject one of those exceptions like we saw before with AMD and so on. How does the TDX module achieve isolation? It runs in a special processor mode called SIM, which stands for Secure Arbitration Mode. And this SIM mode can reserve some memory for itself, and KVM or whatever hypervisor is not able to look at it. This is not very much different from the PKVM model where you have ARM EL2 running the low visor and ARM EL1 running KVM. The big difference is that PKVM is developed in concert with KVM, so they can change the interface between the low visor and KVM at any time, while here it's fixed, and that's one of the issues with TDX. If you look at SEV upstreaming, you can see that it went in phases. Again, the first phases were not really good security, but better than nothing. And it went pretty smoothly. It took about a couple years for each step, but still we had SEV supporting KVM in 2018, SEV yes host support in 2020. In 2022, we got the guest support. The host support was stalled for a long time because of issues with user space API, especially guest memfd, but finally it got in last June. For TDX, we got the TDX guest support about the same time as SMP. We got the initialization of the TDX module also this year, but then nothing else. Why? The main thing is that with SEV and SEVS, we had some choices of developing things in steps. The API that was designed for SEV and SEVS was not perfect, but still we had time to refine it. When we got to SEV SMP, it was pretty clear what we needed, and we fixed a bunch of things in the API that were not optimal. But the main issue is that the TDX module is a really complex piece of software. Talking to it is like thousands of lines of code, not very different from SMP, but a little bigger. But especially the spec for the TDX module is extremely difficult to change, and it does a lot more than the secure processor. There are a lot of complex interaction between the guest and the host that just don't happen on AMD because everything is offloaded to a separate processor. Here, everything is running as x86 code, and that complicates things a lot. Other architectures should be aware. RISC-V, for example, if you want to do something like the TDX module, you will also have some complexity that right now you cannot imagine. So the thing is, if somebody wants to develop for KVM, for TDX, this could be a strategy. You just wait for support to be upstream and then do your thing. But then you've been sitting already for 2 years waiting for KVM support to go in, and it will be a while more. Like, it's not a great solution. So what do we do? There's two things. Both Intel and AMD have their own kernels where they preview stuff that they want to push upstream. And sometimes those kernel sources are actually packaged by your distro. But even that is not really a complete solution. The vendor kernel sources, they are not developed in the open because they are just their vendor repo somewhere on GitLab or GitHub. They are sometimes rebased to new kernel versions, but it's not clear what is added, what is removed, what is stable, what is less stable. It's not clear what has been posted upstream, what hasn't. So it's not a good idea to just take the sources for GitHub and put them in production. Also because you will have to do the stable backports yourself. Just not a great idea, you can get it. And distro also have to make a pretty hard choice, because if they build packages from the vendor kernels, they have exactly the same issue that if you did it yourself. Like, you get it from the distro, but the distro is also not knowing what has been added, what has been removed, and what is upstream and what is not. On the other hand, if you want to curate the set of patches, it's a lot of work, but somebody has to do it. And here is where the beaver comes in. So what do beavers do? Like, you could think that they build the nice little dams for themselves, and maybe they do, but they actually have a huge role in ecosystems, like in natural ecosystems, because dams slow down the river, they prevent erosion. They also tend to flood the surrounding area, which is something that people that want to build houses really hate. Kind of like developers hate the distros. Like, you can see the metaphor works. But for but like the beavers create an environment in which other species of mammals, amphibs like frogs and all that stuff, they really thrive in those wetlands. And the wetlands also stop wildfires, so they make everything easy to live in, and they help the ecosystem ultimately. Like by slowing down things, they help. And this is what ideally you want a distro to use. Of course, you can use Arch Linux if you want. Like, I'm not talking bad about rolling release distros, but if you are developing, maybe you want something slower that you have more control on. And that means basically using stable kernels. And there are two approaches. One is just to have upstream long-term stable kernels, or another very different approach to having a stable kernel is what goes on in CentOS Stream. There are more similarities between the two, as we will see shortly, but they are also very different in how they work. Like, for example, between RHEL 9.5, which is what is used in CentOS Stream, it's basically the same as the RHEL kernel. It has had, in 2.5 years, about 100,000 commits on top of what was 5.14. Doesn't look like 5.14 a lot anymore. It's like 40% of what went upstream also went into the CentOS Stream kernel, but it's still called 5.14. By comparison, 5.15 right now has about 15,000, and an end-of-life kernel like 4.14 had 25,000 over the whole life. Now, RHEL is also going to slow down pretty soon, but still you can see that it's like an order of magnitude almost difference. Why is this? Because it's what we affectionately call a Franken kernel, because it's built from very different pieces, like all put together. So it started indeed as 5.14 back in a couple years ago. But then if you look at RHEL 9.0, there was already some things added from more recent kernels. Some subsystems, they didn't really care about it. Others, for example, networking or XFS, backported little things here and there from 5.16. And if you look at what is going on now, almost all the subsystems have something resembling 6.9 code in them. Some of them are a little behind. Some of them are a lot behind. Some of them that are more sensitive to what Red Hat customers might not appreciate, they just got bug fixes, and they are still at 5.14 level. And in some cases, we really go beyond what is the target release for a given RHEL minor release. KVM, for example, has SMP support, which was backported from 6.11. So not everything in 6.11, but something. So you can see that it is a very monstrous thing. Like, don't try this at home, but it works. You can like it or not, but if you have the money to do it, you can do it, and there are some advantages. So what goes into this kernel? A bunch of bug fixes, a bunch of feature backports, and a bunch of really mass backports that update the whole subsystem to a new kernel release. They have like different sizes. Bug fixes can be just one commit, and mass backports can have hundreds. What's this? Okay. But in the end, despite this difference, it's not very different from what goes on in the stable kernels. Because usually the difference is that with stable kernels, as you develop your program, your software, maybe for 2 or 3 years, you just update to new kernel versions. Once you want to do maintenance, you stick to a LTS kernel, and you just update the LTS kernel. Instead, in CentOS, you will have 5 years of full support, but the first 3 years are a lot faster than the next two. Like after 9.6, as I said, things will slow down a lot. And then there's 5 years of maintenance, where the binaries are available to Red Hat customers to RHEL, but the source is there. Like the source is still available in GitLab if you want. So they provide a very similar product development cycle. The difference is just that with the stable kernels from upstream, you don't really have a choice. Like, it's everything in a release and you get it. While every 2 or 3 months, while with the CentOS kernels, like, it's developed with 6 months sort of cadence that alternates between the mass backport phase and the stabilization phase. Why would you do that? There is some more guarantees of stability. For every patch and backport that goes into the CentOS Stream kernel, there's at least 3 people. One of them is the guy that did the backport, but 2 more that took a look at least at the list of the patches. There are CI bots that look at all the upstream fixes tags, guarantee that those are either included or waived. If something is deviating from upstream for whatever reason, the people there that approve the merge request check it by hand. There is quality testing done for each merge request, at least some kind of sanity smoke testing, but often more. And the sources are available on GitLab, and also the packages can be downloaded through DNF if you are on a CentOS Stream release, or on Koji if you just want to see what it's like. So it's a completely different model from the upstream kernel. This is made possible by good upstream practices like having commit messages, having well-defined boundaries between maintainers, and having topic branches so that we can see what was going on and see the way that merges went into the various, merge commits appeared in the various trees. So this would not be possible if it was not for how Linux is developed. Like it's not, it's a lot of work, but it's work that is possible because Linux upstream is doing good things. And downstream, we have a lot more planning. We have a lot more infrastructure with like CI. This CI is also applied upstream, like the continuous kernel integration system from kernelci.org. There's also bots that do all the checks. And we use different tools. You may agree or disagree on doing development by email, but personally, I think that doing development by email is also part of what ensures that we have commit messages, well-defined maintainer boundaries, and good use of topic branches. And downstream, instead of doing on GitLab, and to be honest, I don't think it would be possible to do that thing with email. So to each its own, like different things have different tools. So we have, for example, this CentOS TDX packages that start from the CentOS Stream kernel. They add the TDX patches on top. It's maintained by me, Camilla, and also Cole Robinson did some work in the past. And it has some recent, currently is about 1 year old, but that's because a lot of changes went in, and it made it really hard to rebase everything. So we are still on slightly older patches for TDX support. But we also include the common code. So those patches are rebased on top of 6.11. They use all the upstream GasMemFD infrastructure, for example. We have the same advantages, sort of, that I talked about earlier with the CentOS Stream Franken kernel, where you can have some kind of review of what's going in. It's done on a smaller target. It's done on a moving target. And the good thing is also that it's very integrated with the rest of the distribution. It grows together, and it helps testing what will be in the next release of RHEL. And it's pretty stable and easy to use for development. Generally, again, we stay faithful to the mailing list postings. We just rebase to whatever we got from the Franken kernel upstream. And of course, because it's all integrated between kernel, QEMU, and libvirt, we try to have a consistent API in the BI. Sometimes we have localized hacks so that you don't have to update kernel and QEMU in lockstep, but those are all in the GitLab sources and available kept separate so that you can look at what is done to ensure this interoperability, and we can always remove later when they're not needed. The packages are on a different instance of Koji called the community build system, which is specific for the CentOS SIGs. Very quickly, if you look at how many patches were added, you can see that sometimes there are some bumps, and it looks like the upstreaming effort is stalled because you see it's like gone down in the beginning, but not much in the end. But actually, if you look at it better, you can see that this blue line is the non-upstream patches, and it did go down a bit slowly, but it did. And some of the growth instead is done because we are including already what will be in RHEL like 1 or 2 months from now, basically. So It's going down slowly, but it is going down. And I think we will cross 200 very soon, like will be 180 patches, sort of, very soon. So in that case, we added the RHEL 9.4 KVM backport. And here it's when we rebase and the backport was merged. You can see that the number of patches that are upstream patches included in this kernel, it went down a lot because this moved from the CentOS TDX kernel to the actual CentOS kernel. So why is this helpful also for upstream and not just for developers of things like Kata containers? Basically because we try to have a minimal set of downstream patches. We try to limit to what is being actively discussed upstream. And we identify anything that is required, but at the same time, it's not being posted upstream. Like we start from the vendor kernels, we trim it down, and sometimes some things come up and you say, what is this thing? We analyze it, we check if it's upstream, and maybe it was forgotten. We talk to Intel, or we just post the patches upstream. Sometimes we redo the patches in a better way. It's like I said before that curating the set of patches is a lot of work, but it's beneficial not just for CentOS users, also for upstream development. And again, as I said before, for people that work on Kata containers, there's one source for kernel, QEMU, and libvirt that can work together and that you can use to develop. Don't really have time for questions, but I think it's best if I leave it to Fabiano now for the next talk, and then we can have questions together at the end.